So we had these regeneration times, and from the regeneration times, we split things into RAD pieces, and then we get lots of large numbers, the conversions. So we proved the following things. Now this is still about my diffusion process solution of some equation. With a reversible part, which I'm writing now. And the addition of deterministic, drift in some fixed direction. Omega lambda 0 of t starts at 0. And what we saw is that we may increase the dimension by 1, considering that process, whose first coordinate is the diffusion process, and second coordinate has a Brownian part, plus some additive functional. So f of omega lambda of s. Yes. Okay. And then so what we proved last time using regeneration times are lots of large numbers. So in particular, Q, P, almost surely 1 over t times the position of the diffusion, so x lambda omega 0 of t converges to something, L of lambda. And you can express the limit in terms of the regeneration times. This is the expectation. So I'm writing this expectation on canonical space. So this is the expectation of the position at time tau 1 lambda, which is the first regeneration time, given, we don't backtrack, given d is infinite. Now, when I thought about this lecture today, I thought it was a big mistake not to indicate that d depends on lambda. So the backtracking time is the time it takes for the diffusion to hit a point which is at distance minus 1 over lambda or something like this. So it does depend on lambda. And then this should be divided by time. So the expectation of tau 1 lambda, also conditioned on the fact that we don't backtrack. And then there are also lots of large numbers with similar expression for the limit when you include the additive functional, and also central limit theorems. So as far as lots of large numbers are concerned, we can prove that 1 over t, the integral from 0 to t, f of omega lambda over s ds has a limit. So this limit, we gave it the name u lambda of f, and this limit is the similarly to that expression, the expectation of the additive functional, so AF at time regeneration time, given we don't backtrack, divided by the mean of tau 1 lambda. Now, you remember that this construction, so we can prove that in for two classes of functions when f is local and let's say either bounded or in the space h minus 1 infinity. And I'm using the same letter nu lambda of f in both cases. And then you remember that when we constructed the regeneration times, this tau 1 lambda, it may not exactly be the same. I mean, okay, at least in the construction with the additive functional, the definition of tau 1 lambda involves f. So here tau 1 lambda depends on f, and we have different estimates on the law of tau 1 lambda depending on the assumption on f. So in particular, if f is local end in h-1 infinity, then we prove that the regeneration time is of order 1 over lambda square, in the sense that we have exponential taste on that scale. And if f is local and bounded, then we don't have such an estimate. And this is also true in the law of large numbers here. Okay? And now, just as we prove the convergence, we can also get central limit theorems. So there are central limit theorems in both cases. Okay. So there are central limit theorems, which also follow from the fact that the regeneration times can be used to split things into RAD parts. So as far as x is concerned, this is just the fact that 1 over square root of t x lambda omega 0 at time t minus L of lambda times t. So this converges in law to some Gaussian random variable with a certain covariance. Let's call it sigma lambda. And this sigma lambda has an expression in terms of regeneration time. So this is the expectation of the position at time to 1 lambda minus, so okay, I should evaluate it in the direction E. So then I will have E dot this thing minus to 1 lambda L of lambda dot E squared, given d lambda is infinite, as before, and then you divide by time, by the mean regeneration time to 1 lambda, given that d lambda is infinite. Okay. And similarly for an additive functional. So here what is interesting is the case where f is in h-1 infinity, and local, say. Then there is also a central limit theorem, so 1 over square root of t. Now, the integral from 0 to t f of omega lambda over s ds minus the mean, which is in the limit, which is nu lambda over f. Okay, then this converges in law to a Gaussian random variable with a certain variance, sigma, which depends on lambda, and it also depends on f. And we have a similar expression. So sigma lambda over f is given by the expectation of the additive function af at time to 1 lambda minus to 1 lambda times nu lambda over f squared, given d lambda is infinite, divided by the mean time. Expectation of to 1 lambda, given d lambda is infinite. Okay. So these are statements that we get from the existence and the estimates we have on the regeneration times. Is it okay? Now, so that proves the existence of steady states. That proves the existence of what we define to be steady states. And we had two definitions of steady states, definitions 1 and 2. And here we have the existence of the steady state, nu lambda, in both definitions. In definitions 1 n2. Okay. So now,
there is an E missing in front of mu lambda F, CLT.
yeah. Indeed. Okay. Okay, thank you. Okay. So this is part of the description of what happens for a fixed lambda. And so the program for today's lecture is to let lambda tend to infinity. To 0. Yeah, okay. Can we let lambda tend to infinity? I don't know. Maybe, but maybe that's the right point to record that the statements which are on the blackboard were actually proved when lambda is less than 1. So, okay, so if we have time, we will let lambda go to infinity, but for the moment, we will discuss the case where lambda tends to 0. And there are different questions, and of course, one question is about this fluctuation-dissipation theorem or relation that we want to address, which is about taking the derivative when lambda tends to 0. But we already have quite a few things that will help us understand what happens when lambda tends to 0, because we already discussed some scaling limits in the regime where lambda tends to 0 and time tends to infinity at the same moment. And I will record that in a few minutes. And we also have some information on the behavior of regeneration times when lambda tends to 0. So, in particular, one first thing we can do is to use that in order to make the conversions towards new lambda, or the conversions there also, but let's say this one, a bit more quantitative. So there is a more quantitative version of the law of large numbers, which I'm going to write. So I will write it for the position of the diffusion, but the statement would be the same for an additive functional when f is in h-1 infinity. So what I mean by this is the following thing. You look at the position of the diffusion at a certain time t, and we want to let lambda tend to 0 and t tend to infinity together. Then in terms of t, this is of order t, and in terms of lambda, we already discussed the fact that this should be of order lambda. So the right normalization is by lambda t, and we want to compare that with the limit that we get from the law of large numbers, which is the speed, L of lambda. So that's for x of t divided by t, but then we also have to divide by lambda. Okay? And that's the quantity that we want to control. Let's say the modulus of it. And what we can do is compute its variance, for instance. Well, compute the variance, or compute the limit in probability, but okay, the variance is okay. Okay. And then you expect that to be small after a large number of regenerations. So the regenerations take place on that scale 1 over lambda square. So we should send time to infinity and lambda to 0 in such a way that we are on that scale lambda minus 2. So the assumption is that lambda squared t, let's say, equals some number alpha. And if I want to use the regeneration picture, then I want many regenerations to take place. So I should take another limit when alpha tends to infinity. And so, maybe strictly speaking, it's better to take a limit up here. And then the quantitative version of the law of large numbers is that this is 0. So if you scale things in this way, and I just tried to explain that this was the natural way to scale things, then you can approximate the position of the diffusion at time t by its limit in terms of, as the law of large number indicates, and it will be a good approximation if you look at it on scale lambda minus 2, and you furthermore send alpha to infinity in order to be sure that you have a large number of regenerations. So that's one statement that you can do. And then there is another statement which is exactly the same for an additive function. So there is a similar statement. If you replace the position of the diffusion by some additive functions, the integral from 0 to t f omega lambda of s ds, and then you replace L of lambda by nu lambda of f. So in the case where we have a good control of the regeneration time, so that is when f is in h minus 1 infinity tilde. Then you just replace and you get the same conclusion. And actually the argument to prove that is the same. So okay. Now okay, let me sketch where this comes from. It's not mysterious. It's a little bit of it's a not so difficult technical exercise to check that. But okay. So I will be a little bit sketchy. There is what you do is you split the trajectory into IID pieces. So there are some parts which are very easy, because if you look at things like, if you look at the variance of the position of the diffusion, so now I'm moving to past space because I'm using the regeneration time, therefore I'm using the canonical process. So, I mean, of course, if you look at what happens after k regenerations, and you look at the variance of this, so everything being computed under p lambda, this is very easy, because this is just a sum of IID random variables. So there is the first one, which is a little bit different, but it doesn't matter. So anyway, when you compute the variance of that, this is easy. So, for instance, you would check this way, that when you compute the variance of, so let me write first like this, x at some time to lambda, and then I will adjust k, and it will depend on time t. I want to compute things at time t, and I divide by lambda t. So this should be for the L of lambda divided by lambda. That's what we expect. And this you can easily bound by the number of variables here, which is n of t, and you have to divide by lambda squared t. So how do we choose n of t? N of t, we choose it to be t divided by the mean of the regeneration time. So the expectation of tau and lambda, given that d lambda is infinite. Okay, and then n of t is of order lambda square t. So here we have lambda square t. We divide by lambda square t square. So this is of order 1 over t. This will tend to 0. Easy. And then you have to compare tau lambda n of t, which is a number, yeah. You have to compare that with t. And I say that you can compare, so this is supposed to be of order t, and I mean, it is t plus minus epsilon t for any epsilon with large enough probability, with probability tending to 1. So for all positive epsilon. And this is the same thing. This is a computation of the variance because this is also a sum of highly random variables. So that's also not difficult. And then you should compare x at time t and x at time tau lambda n of t. So we want this to be not too big. Now, with huge probability, we have that tau lambda n of t will be t plus minus epsilon t. So if we compute the variance of this on the set, on the event where tau lambda n of t minus t is smaller than epsilon t. This is a dangerous part, if you want, of this. And then you have to bound this guy. Okay. And so this is controlled by the fluctuation of the diffusion process on a time interval of size epsilon t. And you can control that by saying that on a time interval of size epsilon t, then x, let's say, fluctuates at most of something of order lambda epsilon t. Okay? And that comes from a priori bounds that we had on the speed at which the diffusion can escape. So we already discussed that in lecture number 3, or lecture number 2, I guess, where we discussed the fact that the process X on a time interval of a certain length, it can make a fluctuation of linear with time and linear with lambda, but not bigger than that. So here we have a fluctuation of this on this scale. And then you see this is okay because actually what we really want to control is x of t divided by lambda t minus the same thing. And we divide by lambda t. And then we will say that, for instance, the variance of that on that event will be bounded by lambda epsilon t divided by lambda t, which gives an epsilon. So at the end, we choose epsilon to be small, and then we are done. Okay? And so that is the sketch, if you want, of the argument. Okay. And now, if you want to use the same argument, and we do want to use the same argument for an additive functional, like this, then you can use the same thing for the first line. So you just split in IID pieces. So along the regeneration times, you have a sum of IID random variables. So that gives a control of the variance at regeneration times. That gives a control of the regeneration times themselves. And then you have to argue in a similar way as here. So what you will be using is the fact that you also have this property that on a time interval of size epsilon t, then the same thing is true for an additive functional. And at that point, it is important to record that we are assuming that f is in h minus 1, h minus 1 infinity, because otherwise we don't know. I mean, and actually, it would be wrong for a bounded f, for instance. Okay? So that statement that AF fluctuates at most by something of order lambda epsilon t on a time interval of size epsilon t is, here it's correct because we are assuming that f is in h minus 1 infinity. So the assumption that f is in h minus 1 infinity appears at this stage of the proof. Now, take a look. Okay. And then we get this kind of quantitative version of the law of large numbers. Okay, so this we don't need anymore. When I started the course, I said that one ambition was to get the scaling limits of this process, x. And now this part is kind of complete now. So in the previous lectures, we described the limit of the process x lambda omega of t divided by lambda t on the scale where lambda squared t equals alpha. So I mean, if you recall for the first lecture that the scaling limit of the process lambda x lambda omega 0 of t on the scale where time is scaled by lambda square. That is something we already did. Actually, we did it for that process. We also did it for the z process. So z lambda omega 0 at time t over lambda square. So it exists, and this is Brownian motion with a constant drift. So that's, I mean, for a fixed time. This is this process. Maybe I should not use the letter t for that. But okay. So in the previous lecture, we saw that the scaling limit on that scale is given by Brownian motion with a constant drift, and this is the information that we can get from homogenization theory using the Gersaint transform. And so we have a description of this limit, and we also have this quantitative version of the law of large numbers, which tells us what happens when you work just above that scale. That is, you are in the scale lambda squared times equals a constant, but this constant is big. And then we see that the correct description of the process is just what you would expect from the law of large numbers. So you have this kind of two extreme regimes. The one corresponding to lambda equals 0, where you have a diffusive behavior. The one corresponding to a fixed lambda, where you have a ballistic behavior. And somehow these two regimes extend. So the diffusive regime extends up to that scale, lambda squared t equals a constant. And the ballistic regime still gives the right scaling limit on that scale. So lambda squared t equals a big constant, let's say. And then in the end, they overlap. They almost overlap. There is no room in between the diffusive regime and its extension, if you want. I mean, the homogenization theory describes a whole range of parameters. The ballistic regime describes, the law of large numbers describe a whole range of parameters, and they overlap. So there is no room for something in between. I think that unlike many examples of stochastic and non-stochastic systems we have, where we have, let's say, a subcritical phase and a supercritical phase and a critical phase in between, and the subcritical phase has certain features, and the supercritical phase has a certain number of features, and they are well separated, and these features are quite different. So here we have a different picture, because the two regimes almost overlap. Okay.
Talk about scaling limit, you're looking at finite time intervals.
Now, do they really overlap or not? That's too philosophical question for me. But well, what I can do to answer your question is give you one example of what I mean by the overlap. So let me write a consequence of this. So for instance, okay, so I'm going to give you a proof of the Einstein relation from that. Now, actually, before I do that, I should finish recalling this statement, because not only did we prove that the scaling limit on that scale is a Brownian motion with a drift, but we also computed the covariance and the drift part. So I write the covariance and the drift part for Z, for the process Z. Then the covariance is given by 1. So there is some matrix, sigma, which is the covariance of X. But this is just the limit of covariance of X. The non-diagonal terms vanish for symmetry reasons, because X is antisymmetric, and the additive function AF is symmetric. And that here is, so there is a 1 corresponding to this small W1. And then you get the asymptotic variance of the additive functional, which I think we denoted by sigma of F. There is no information in this matrix, right? This is the definition of sigma and sigma of F. And then there is the drift part. And the drift part is, so in the X direction, this is sigma applied to the direction E1, the one in which we have the force. And here we have some operator which we call gamma bar of F. And this gamma bar is of F. In fact, this is a covariance. So, oops. I should find. Okay. Let me write it here. So this gamma bar of F, you can view it in different ways, but one way to see it is this is minus the limit as time tends to infinity, 1 over t times the expectation of the covariance between the additive functional, so the integral from 0 to t f omega of s ds, and the drift part in X, which is the integral from 0 to t b omega of s ds. So b, in fact, in direction E1. So E1 dot b ds. Okay, this gamma bar appeared as a covariance, as a limit covariance, and this is the covariance between the additive function we care about and the drift part of x. And there is a minus sign. I guess this is correct. I tend to forget 1/2, but here I don't think there is a 1/2. Okay, so I said the covariance matrix doesn't bring any information. The drift part is more interesting because once you know sigma, then you actually know the drift part of this process, and this gamma bar. So we check that it is given by this expression, but this does not. Okay. Something should be proved. Okay. So now let's go back to the Einstein relation. Anyway, I'm only going to use that theorem in the case where you only look at the x component. So to prove the Einstein relation, so this is part of the program, we want to take the derivative of L of lambda. And the claim is that this is, when I let lambda tend to 0, this is going to converge to sigma E1. So I claim that this goes to 0. Now, we can deduce that from what is written on the auto blackboard by saying that we will bound this difference by comparing 1 over lambda L of lambda with the mean position of the diffusion at some well-chosen time t. So this we compare with the expectation of x lambda omega 0 at some time t divided by lambda t. And we also compare sigma E1 with the same thing. So okay, I write things. I will get the Einstein relation by saying that I have two ways of computing the expectation of x lambda omega 0 at time t divided by lambda t. One way is from the law of large numbers, and then I will compare this expression with L of lambda divided by lambda, like here. Okay. And then I have another way, which is to use this scaling limit. Okay. So you see, you choose t so that lambda squared t equals alpha for a certain alpha. And then you let lambda tend to 0. So take the lim sub when lambda tends to 0. Also in the right-hand side. Then I can use the scaling relation. So I can use this statement. Okay, I am in this regime. I look at this term, and then I say, okay, so in this regime where lambda squared t converges to some constant, that guy converges to a Brownian motion with a drift. I'm actually only computing the mean, so I get the drift. And the drift is sigma E1, so that term vanishes. So that one is 0. And then you are left with this one. You can freely choose alpha. So you take that term, take the limit when alpha tends to infinity, and you get 0, and that comes from the law of large numbers, which is there. Now we are in that regime where we are sending t to infinity lambda to 0 in such a way that lambda squared t converges to a large constant, and then once we take the limit when alpha tends to infinity, then that term also vanishes. Okay? So that is what I mean by the fact that two regimes overlap, because they both, in both limit theorems, the two limit theorems which are over there, they can be both applied to compute the same quantity, which is just the mean divided by lambda t, and in particular the Gibbs relation. And somehow the Einstein relation expresses a consequence of that. That is, there is nothing but the ballistic and the diffusive regimes. So I think that it's a general idea that the Einstein relation. So I don't know whether you really care about proving the Einstein relation itself or not, because one can discuss whether it's how interesting it is to be able to compute the derivative of the field. Sometimes it is. In some examples it is. But another aspect of the Einstein relation is that probably, I mean, you can also see the Einstein relation as a manifestation of the fact that the situation, you don't have any surprising regime in these models. The diffusive regime and the ballistic regimes describe everything. And so maybe the gap, let's say, in an example where the Einstein relation will not hold, then it probably would be an indication that something else than the diffusive and the ballistic regimes exist. Okay. So, in fact, this argument is the first proof of the Einstein relation we gave in the paper with Andre and Nina. And I would like to move to another one, to another proof, which will also use the regeneration times. Now, why get another proof? So, one motivation for this, okay, maybe because it's interesting to have another proof, a slightly different proof. One question that remains open when you do that is about the diffusion matrix. So there is one question, which is, do we have the following? Now, for a fixed lambda, there is a central limit theorem, and in that central limit theorem, there is a certain limit covariance, which I called sigma lambda. And you can ask what is the behavior of sigma lambda when lambda tends to 0? And if you are optimistic, then you believe that sigma lambda should converge to sigma. So that's the question. Okay? So once again, the sigma arises from what you see with lambda equal to 0, and then you are in the homogenization setting. So the sigma arises from homogenization theory, if you want, and that sigma lambda comes from the regeneration. So these things are the existence of sigma lambda and the existence of sigma, they come from very different pictures. But however, you might expect sigma lambda to converge to sigma. So the answer is yes. And I don't quite know. Well, I'm not sure I could prove it using this kind of argument. It's not, okay. I don't say it's really impossible, but I'm not sure. Anyway, so we will get that anyway using a slightly different approach. That was using this theorem combined with estimates on regeneration times. So let's say this is a slightly different approach to get the Einstein relation, fluctuation-dissipation theorem, and also the continuity of the variance. So let's say another approach. Okay. So here I need a couple of steps. Actually, here, the technical part of this argument, so to speak, is the exercise. So last time I gave you an exercise. And now it's when we need this exercise. So we have a process, H, which is nice, bounded, whatever you want, and in such a way that H of M is f lambda minus 2m measurable. And the exercise was about computing the expectation of h at time lambda square times tau 1 lambda on the conditioning on non-backtracking. Okay, so I will give you the solution of the exercise. What makes I mean, you don't think I should give the solution of the exercise?
No, I'm not. I don't have any responsibility to this lecture.
No. Okay. I mean, anyway, it's not very long. So, what? Sorry?
I want to prove that your expression is valid. I think it's okay to just give an expression. I mean, the exercise was to find something inside the expression. No, in the.
Yeah. I can spend 5 minutes on it. Because okay, it won't be long anyway. The exercise is not very difficult. So let's say I want to compute this thing. So first thing we do it by conditioning. Okay, one reason why I give the solution is because I want to recall how the regeneration times are defined. And so I condition on k, which is the number of times we run the algorithm to define the regeneration time. And then we get the sum over k, and we have to write. Okay, so when k equals small k, then the regeneration time is of the form S lambda k. And then we have the indicator function that S lambda k, that bk equals k, but we are also conditioning on the fact that d lambda is infinite. So we'll have the indicator function that d lambda is infinite, and we have to divide by the expectation. In the probability, what is the expectation of the indicator function that d lambda is infinite. Okay? And then you look at what it means, this thing. So on that thing, we have k equals k, and d lambda is infinite. Okay, so from time 0, the process does not backtrack, and it does a certain number. You run the algorithm a certain number of times, so you know you're not going to backtrack. You run the algorithm a certain number of times, and at some point, you say how this is some S lambda k, and then from that point, I'm not going to backtrack again. So here, what we have here is that we run the algorithm k times, so S lambda k is finite, and then after that, we don't backtrack. So T composed with time shift d lambda S lambda k is infinite. And that is if and only if. That is, if you can run the algorithm k times before the regeneration to take place, and then you don't backtrack, then that means after S lambda k you will not backtrack, but before you also didn't backtrack. So this is a true equality. It's not just that one is contained. Sorry. It's not true what I said. This would be an implication, but what I wanted to write is that S lambda is less than d lambda. and now it's going to be, okay, and now it's correct. So once again, if you reach the regeneration time after k steps and you don't backtrack, then in particular S lambda k is finite. You don't backtrack, so d lambda is infinite. So that is just another way to express that S lambda k is finite. And also, because the regeneration is taking place at k, then after time S lambda k, you also don't backtrack. So that this event is contained in that one follows from the definitions directly. But the converse is correct, because what this expresses, first, this implies that you don't backtrack, because after time S lambda k, you don't backtrack. And that also, that condition implies that before time S lambda k, you did not backtrack. So these two conditions imply that one, and then they obviously imply that k equals k. Okay. And now you can compute these things. So you look at this guy over there. So this term, E lambda of h at time lambda square S lambda k. On the event, which I rewrite as S lambda k less than d lambda. And after, so d lambda composed with the time shift at time S lambda k is infinite. Okay, and this is the kind of thing that we want to compute. And okay, so this is an expectation with respect to dq. Now we want to use the Markov property for a given omega. S lambda k is the stopping time. So we would like to use this Markov property. So I condition on omegas, and I have the expectation in the given environment omega of h. Okay, there will be some abuse of notation in this proof, but you will correct it. And I look at what happens until time S lambda k. So I have the integral function that S lambda k is less than d lambda. And now I condition on what happens at this stopping time. So I will get the probability, lambda omega. But now I start the process at the position x lambda omega at time S lambda k. And I compute the probability that I don't backtrack. So we get something like this. Okay? So there is some abuse of notation because I'm using d lambda and S lambda k as if they were defined on. Okay, they are defined on canonical space, but you can also define them on the space of the trajectories of the diffusion. Okay? And so this is the Markov property, the fact that this is a predictable event, and also using the assumption on h. And then you look at this probability, and you say that here you take advantage of the fact that the position at which you are at time S lambda k is something that depends on the environment before, to your left, strictly to your left, and whether you're going to backtrack or not is an event that depends on the environment that you see on your right. So these things split. That is, first of all, this, I mean, when considering the question whether d lambda is finite or not, then using the fact that the environment is invariant by translation, this is not going to depend on the value of the initial where you start from, because the position where you are and whether or not you're going to backtrack, they are independent. So actually this term, you can take it away from that expectation, but also that expectation. Because it doesn't depend, this term depends on omega. Here there is also an omega, but they depend on different parts of the environment. So that term factorizes, it gives a p lambda that d lambda is infinite in front. And then you integrate the rest. So when you integrate the rest, you get E lambda of h at time lambda square s lambda k. Indicate a function that s lambda k is less than d lambda. Yeah, correct. Okay, so that's the computation of one term. Then you divide by the probability of non-backtracking, and so you are left with this term. So the conclusion is that this can be re-expressed as a sum over k of the expectation of h at time lambda square s lambda k on the event where s lambda k is less than the backtracking time. Okay, so this is the formula I want. Is it okay? Yeah?
Could you remind me again why the probability part is, I mean,
This guy.
yeah, it's, I mean, from under that measure, the process see a certain environment.
The process?
Will see certain environment afterward. And that environment depends on its starting point. I mean, you are in the environment seen from x lambda omega s k lambda.
Okay. And the more precise way, a more correct way to write this argument is you condition on that. So if you do that, you add some another integral,
Yeah.
and then so you have an x here, and then
Regular conditional.
yeah, and here I will have the indicator function that x at time s lambda k equals x. Okay, and then you look at what this depends on. That is, what happens is that all this, including the conditioning on x, depends on the environment to the left of x, of the hyperplane at x, okay? And all this depends on the environment to the right of x. So when you integrate with respect to q, the two things split. They are independent. This part, okay? I have something like this, and then I have another integral with respect to dx, okay? Okay? Something like this, okay? And then I say, okay, now let us look at what happens for a fixed x. Fixed x, okay? So you only care about what are the parts of the environment which are involved in the two expressions, and they are different. So I fix x, and then I integrate with respect to dq. And here I have one term, and then I integrate this one with respect to dq. Okay?
No, it's not okay to me because this dx is a regular conditional distribution.
Yeah, so actually
So you cannot.
there is something involved here because of this indicator function. You use the density.
Yeah, but the point is that density.
But that density will be here
Okay.
because it depends only on the left part. Yeah. So I'm not cheating too much. I mean, this is a little bit loose as a notation, but this indicates that you are taking the density or the regular conditioning, whatever, and that part does. That part is included in the part that depends only on the left, and this is important, of course. But that's why it is on this side of the integral, in this first integral with respect to dq, and then what depends on the right part is only this part. Okay? And now, this integral still depends on x, but it does not.
Yeah, but it's once you can.
But it does not depend on x, and then it goes away.
So the point is that regular conditional distribution depends only on the parameter to the left.
Okay, yeah, that's correct. Uh-huh. Yeah. No, I mean, it's a little bit subtle. Well, this argument is already in papers of Slitman, in particular. Not exactly formulated this way, but yeah, I mean, you have to do this kind of thing when you this exercise is maybe not explicitly stated like this, but it's some version of it is used by Stephen. Okay? 大丈夫ですか?
Sorry?
大丈夫ですか? 大丈夫です.
I have one more question, but it's too much detail. And it's not very related to your lecture. Not directly
Okay,
related
so
to your lecture.
we will.
I have a question about variance paper.
Let's maybe postpone it
Yeah, of course.
a little bit. Okay, so let's take a break for 2 minutes. I'm just recording, yes, because I was happy when I wrote it on the board. I thought, okay, I have to keep that. And then I erased it. Okay, so now it's back on the board. So, okay, this we are going to use. Okay. So, it's a slightly different way to get the Einstein relation, but also the continuity of the variance. So based on that, so let's use some notation. So we'll let, what did I write? Curly P and also curly E, thing like this, to be the law and the corresponding expectation for that Brownian motion with that covariance, and that drift. Okay? So let's use this notation for the law of this thing. So a Brownian motion with a constant drift with this value, these values. Okay? And then so an alternative way to get the Einstein relation is based on that lemma, which computes the limit when lambda tends to 0 of the expectation of some function of the position. Yeah, I put the position first. So the position of the diffusion at the first regeneration time, which should be of order 1 over lambda. So then we multiply it by lambda time. But time should be scaled by lambda square. So lambda square times tau 1 lambda and lambda. And say we want to compute the limit of that. And I will normalize. All the quantities we are interested in are normalized by the regeneration time. So I normalize by lambda square to 1 lambda, given D is infinite. Okay? And the claim of the lemma is that for nice enough phi, so I will write the assumption on phi. So phi is a function that depends on space, which is Rd plus 1, time, which is R plus, and lambda, which varies in 0, 1, 0 being included. And what we assume is that phi is continuous, and that phi doesn't grow too fast. Let's say phi has at most polynomial growth. In fact, you could even deal with mild exponential growth. Anyway, so the claim is that this converges to something which is expressed in terms of the scaling limits. So it converges to something that should be written in the following way. This is the expectation, for this law of the same thing. That is, it is the expectation of the value of the process at some time to 1, phi of this, to 1 and 0, given D is infinite, divided by the expectation of to 1, given D is infinite. And in that expression, what these things are, it is the same as before. That is, tau 1 is a regeneration time constructed by the algorithm that we used to construct regeneration times. D is a backtracking time. And you do the construction. Okay, so tau 1 and D are regeneration times. And the backtracking time. And these two things are constructed using the same construction as we had, but you run the algorithm when lambda equals 1. And then they don't depend on lambda anymore. And by the way, this curly E, this curly P, they are the law of Brownian motion with a drift, and Brownian motion with a drift. Indeed, the regeneration time is finite. So these things are. I mean, tau 1 is almost surely finite under curly P. Okay. Now, how do we prove that? This is a direct consequence of this exercise. because you want to compute, let's say you take the denominator, or the numerator, anyway. So you take the numerator, and it is of this form. And then you write this as a sum, and you look at what happens. So you will get, I need a little bit of room, but in fact I'm going to rewrite the same formula, but applied in this specific case. So I take the expectation of phi of lambda z at time tau 1 lambda, etc. Lambda square tau 1 lambda and lambda. And I write that as a sum. So, sorry, forgot to condition. D lambda is infinite. Okay? And then you write this as a sum. So this is the sum over k, and then you will get similar things, where z at time s lambda k, lambda square s lambda k, lambda, with the indicative function that s lambda k is less than d lambda. And then we pass to the limit. So for each k, for a fixed k, if you look at one of these terms in this sum, then you see that everything here is a continuous function of the rescaled process. So, for instance, s lambda k multiplied by lambda square, this is a continuous function, a fixed continuous function of the rescaled trajectory. Lambda z at time dot over lambda squared.
High probability sense because it's escape the heating factor. Instruction of escape contains the backtrack and heating factor.
Yes.
Strictly speaking, it's not a continuous function. Of course, I believe it that it was a problem.
No. You. No, it shouldn't cause any problem. That's correct, but in fact, it is. I think. No, why? I mean, you wait until the first time you hit fixed level. The heating time of a fixed level, and then you do something which is.
You don't use backtrack.
Yeah, in SK, yeah, but even the backtracking thing, because I need the same thing for d lambda actually, but it's also, I mean, this event. Well, okay, this one is not going to be continuous, but it's also certain conditioning on an event which only depends on the rescaled trajectory. So if I was not mistaken, then the construction of the regeneration time is done in such a way that it is actually not, it is really a fixed function of the rescaled trajectory. And then you have to compute first time you reach a certain level.
What do you mean by continuous? What is the topology on path space? Is it L infinity or?
It's the topology of, the standard topology. We have continuous passes, so it's the uniform convergence.
If you shift the path to straight heat,
then you can change the heating time. Then it's a little bit, yeah, you have to have a little bit of flexibility. Okay. No, okay, in that respect you are correct. So okay, we write like this, close to the continuous. Okay. So we're using weak convergence, and the set of discontinuity plays no as measure 0. So then anyway, I would have had a small problem with the indicator function, claiming that the indicator function is continuous. So okay, so it's not really continuous. That's correct, but it's a function of these three scales pass. And also one thing which is not completely correct is that in order to construct the regeneration times, I should have enlarged the probability space, which I didn't write. But for a fixed scale, you can pass to the limit in this expression. And then one is the control of the tail of that. So then, for a fixed scale, it's not continuous, but we can pass to the limit. Okay? And then we need control of the tail. And that, in order to do that, then you need some control on the law of lambda squared times the 1 lambda, and also on that. And this is exactly what we had in the previous lemma last time, that we have a uniform control, exponential control of the tail, and that allows to replace this infinite sum by a finite sum when we pass to the limit without any difficulty. And then we get this expression. Okay. And now let us just write consequences of this. Oops. Okay. So in words, what this lemma allows you to do, it means that when you want to compute an expression like that, you can actually, in the limit when lambda tends to 0, so here lambda tends to 0, then you can replace the computation of any expression like this by computing the same quantity on Brownian motion with the drift. So let's see how it works. Now, say for instance, you want to get the Einstein relation. So you look at the speed. Now, this can be written in that form. So this is the expectation of x at time to 1 lambda. So x being the first component of z. I would like to have a lambda here, so I put it here. And then I have to divide by the mean of the 1 lambda. Also conditioning on d lambda equals infinity. But I divide by this lambda and another lambda, so I get lambda squared. Okay? And then I am in that case where I can apply the lemma. So you can pass to the limit when lambda tends to 0. Okay? And if you do that, then you get a limit, and the limit is this thing. So the limit is what? The same thing as the one we are computing here, but on the limiting process. So here what we compute is the mean, the drift, the mean. So what we will get here is the drift under curly p. That is sigma E1. Okay, so that's short proof of the Einstein relation. Now we can do the same thing for the variance, sigma lambda. So sigma lambda was something like this, the expectation of the 1 lambda minus the 1 lambda times L of lambda. Then we square that condition. Okay, and then we have to divide by the mean. Okay. Now, I want lambda here. So I'll get a lambda squared down there. And here I want to multiply by lambda, but I want to scale lambda square. So 1 lambda should be scaled by lambda square, and then I have to multiply by 1 over lambda. And then I think it's correct. So that case corresponds to a certain choice of phi over there. So it corresponds to choosing phi of So here I don't have z, I just have x, t and lambda, which is so x. Now actually, I always do the same mistake. If I want to have two expressions, I have to choose one direction. So you should put a scalar product with z. And then the function phi is x dot e minus time times L of lambda divided by lambda squared. Okay? And that function is continuous. And it is obviously continuous as a function of x and t, but it is also continuous as a function of lambda. And this is what we just saw, that L of lambda over lambda has a limit. So this, if lambda is not 0, and if you want it to be continuous, and we want it to be continuous, then it should be x dot e minus t, I forgot dot e also here, times sigma e1 dot e squared. Lambda is 0, and this function is continuous. Okay? So we can pass to the limit. So we pass to the limit, and we get something when lambda tends to 0. And what do we get? We get this expression, but you don't want to, you never want to compute that expression. You just want to interpret what this expression computes. And here we compute the variance, so we pass to the limit, and then we get the variance. So we get the variance now under P, and then we read the variance over there, and it's sigma. So we prove that sigma, so it's sigma in direction E. So the conclusion is that sigma lambda converges to sigma as lambda tends to 0, which is not very surprising, but
the definition of phi when lambda is 0. Definition of phi, left bottom.
Here?
Yeah, it should be E dot sigma E, I guess. No?
No, this is E1. E1 is the direction in which you push. Yeah. No, but it has nothing. This has nothing to do with that.
Okay.
We don't care. I have to. Okay, you should know that phi is continuous when lambda tends to 0.
Okay.
Because if phi explodes or whatever, then the lemma does not apply.
Okay.
But yeah, there is a 0 here. But yeah. Okay. Okay, and let's say last thing. Take a function f in h minus 1 infinity tilde, and then compute so the fluctuation-dissipation relation. So we compute nu lambda of f and divide by lambda, and then we do the same thing. So this is the expectation of the additive function at time to 1 lambda, given d lambda is infinite, that we divide by e lambda of the 1 lambda, given that d lambda is infinite. Okay, now I want to multiply that guy by lambda, and here I'm dividing by lambda squared, just like in the case of the drift. And okay, once again, we are in a situation where we can apply the lemma, and we get the limit. And now what we get as a limit is what? This is the drift part of the last component, coordinates, of z under curly p. So we read it here Forget gamma bar. Of F. So this is the fluctuation theorem, fluctuation-dissipation theorem. In that case, in our module. And there is one last thing which is missing, which you can do, is prove that in the central limit theorem, if when you look at the variance of an additive functional with some lambda, then when you let lambda tend to 0, this converges to sigma of f. Okay, but this one I will leave it to you. It's of course the same thing as a computation of the variance over there. Okay. So. Don't laugh when I speak Japanese. It makes me feel very uncomfortable. Was there anything wrong with the question? With the formulation of the question? No, it's okay. So, shitsuma narimasu ka? Okay. So now we, what did we do? We completed our program, didn't we? Okay, so let me erase. And I don't really have time to embark in something really new. Yes, that would take more time. Okay, so I'm sorry, but I'm not going to discuss the case lambda tending to infinity. There is one thing I skipped from the first lecture, actually, which is this discussion about gamma bar. So there is some connection between gamma bar and the corrector. So we don't actually need that in order to do the proofs, but the corrector is a natural object arising in homogenization theory, and there is a simple way to connect the corrector and the operator gamma bar. In the definition, in the first lecture, so as I wrote before, gamma bar of f appears as a certain correlation. So I write sigma for correlations, and this is a correlation between the additive functional corresponding to f and the additive functional corresponding to the drift term in direction E1. So by definition, this is just minus what we had before. Limit as time tends to infinity, 1 over t, the expectation of the product of the additive functional and the other additive functional corresponding to b of omega lambda s ds dot E1. Okay. Now the corrector, Kai is the corrector. So what is the corrector? So first of all, the idea about the corrector is the following. Let's say chi is going to be a function that depends on space and randomness. So chi is a function of x and omega. And let's say I want to prove the central limit theorem, but I'm not going to use Kipnis and Varada. I'm going to do it in a slightly different way. I still want to find martingales, so the question would be find a a function of space and randomness, such that when you look at the diffusion without lambda, so you look at x omega 0 times t, you add this corrector, so you add the correction. So you add chi evaluated at x omega 0 of t and omega, then you want this to be a martingale. Now, once you found a function like this, such that this sum is a martingale, you are really in business to prove the central limit theorem, because this martingale will, okay, then you will have to check that you can apply the central limit theorem to that martingale, but this is not the difficult part. So let us look at what it means that something like this is a martingale.
Excuse me. I think the gamma f, the expression gamma f has a limit.
Yes, yes, I'm listening to you.
No. I think f expression should be f of omega s.
Ah, yes.
That's it.
Always. Yes, yes. Thank you. No, there shouldn't be any lambda in all this discussion. So, yeah. So we look at this condition and what it means. We have a Markov process, so to be a martingale is the same thing as a generator vanishing. So you look at the drift part, and the drift part arising from chi is going to be the generator applied to chi. So 1/2 div a omega grad chi of dot omega. And we want this term to cancel the drift part in x, which was b. So this should be b omega of dot. And b omega was 1/2 of the divergence of a omega of dot in the direction E1. So that's one thing. And then possibly, okay. Everything is vector valued, and okay, everything is vector valued, but maybe that's not a problem here. Or maybe that's a problem. So I will express this by taking the scalar product with a fixed vector. For all. Okay. So I can cancel the 1/2, and then I have to reorganize this. So I want to reorganize this in the following way. Let us write that this is the same thing as saying that the divergence of a omega applied to well, I don't know if I need the E, because I have no, this E1 does not exist. Okay. E, which comes from there, minus E dot grad chi dot omega jack equals 0. So I guess this is okay. Okay. So we are looking for a chi that satisfies this equation. And the idea is you look at this equation as an equation in grad chi, then and solve it on omega. So to construct chi, let's say you have two steps. So step one, now you find grad chi on omega, because you see everything is stationary here. So you can make this equation. This is the equation for grad chi. You can lift it to omega, or project it to omega, in fact. and then you will get some stationary solution. And you will, because what we are expressing here is the fact that the divergence of something is 0, which means that this something which is there is in the orthogonal of all gradients, and we are looking for a gradient. So actually, this is an orthogonal projection. And this is an orthogonal projection in a space of fields which are locally of gradient form. And then from grad chi, we have to construct chi. So the second thing is you go to RD, and then on RD, so you look at the, let's say you fix omega, and you look at this field, grad chi, applied to x dot omega, but you look at the function of, at this as a function of x, and then this is a one form, and this one form is exact, and then it's, I mean, this one form is closed actually. It was already closed on omega, but it's closed, and then it's exact, and then you can integrate. So from that, you construct chi. Okay? So, and how do you explicitly construct chi? It's something like chi of x omega or omega x omega. This is the integral from 0, say, to x of grad chi of dot omega. And you integrate along any path that goes from the origin to x, and the result will not depend on the path. So this is any path from 0 to x. Okay? Or you can make another choice. Here I just chose that the corrector should vanish at 0, but I could choose that the corrector... okay, there is some choice to be done. Okay. And then let's say the whole approach to the central limit theorem or something like this from homogenization theory is to prove that chi has a sublinear growth, so that when you look at x plus chi, and when you divide by square root of t, then the part corresponding to chi will vanish. But this is not what I'm discussing here. What I wanted to discuss is just the fact that we can indeed construct a corrector, and this way, and I want also to stress the fact that in the construction of the corrector, we have a stationary field which is its gradient, and we have a not necessarily stationary field which is chi, which, for instance, in that definition is not going to be stationary because it has this property that at 0 it vanishes. Okay? So we found chi, and the chi we found has this property that grad chi is stationary. And chi itself, well, okay. If I take this definition, there is no chance it is stationary. But in general, you could ask, can I choose a stationary chi? Because, I mean, if you are lucky enough, then maybe you can choose a stationary chi. And I don't quite know the answer to that question, except for the fact that in discrete models, so on ZD, when D larger or equal than 3, and the environment, so Q is IID, so for instance, this is one situation where you can actually choose a stationary chi. So in general, there is no hope to choose a stationary chi, but even in dimension 2, it should not exist, a stationary corrector. But under strong enough mixing conditions on the law of the environment, and if the dimension is larger or equal than 3, then, for instance, when Q is IID in the discrete models, then there is a corrector. The corrector, a stationary corrector. And this is proved by Gloria, Nuckman, and Otto. And then there were, many results from quantitative homogenization extend this. But, okay, the diffusion case is, things were proved in the discrete case. I'm not sure about the proof in the diffusion case. Okay? And now, anyway, Oh, okay. Then there are different ways to argue. Okay, so we have to deal with the fact that chi itself is not necessarily stationary. However, so the connection between gamma bar, let's just write proposition, and the corrector is the following one. Gamma bar of f, so f is in h minus 1. You can, let's say, one way to write this would be to say that gamma bar of f is minus 2. So I didn't even write this formula, but so minus 2 times the integral of f chi dq, I guess. Okay. This doesn't quite make sense because chi is actually not defined on omega. So we forget about this expression. So I'm going to erase it, but I will write it down. And we replace by finite time approximation. And then we get the expression, the expectation, 1 over t times the expectation, the integral of 0 to t, to f of omega of s. Yes. Well, maybe before the s. Chi evaluated at x0 omega of s omega in the direction E1 ds. Yeah. And this is the limit at time, as time tends to infinity. So you see, okay, this expression has a sense. It has a meaning. Okay. So that is not difficult to prove. So I will not give the proof, but the proof is just a couple of lines. You play with the symmetry. So you play with symmetries. So you write that here you have a symmetric additive functional. When you look at x and chi, they define antisymmetric additive functionals. So you write some orthogonality relations, and you compute this limit, and computing that limit, you find that this limit is sigma of f b dot E1 with a minus sign, which we know is gamma bar. So just to conclude, back to that expression I first wrote and then erased. So let's say remark or comment, if chi was stationary, then we could use the ergodic theorem. Well, not even the ergodic theorem. We would just use the stationarity of the environment in order to express this thing which is over there. And then what we would get is something which is wrong because this time I did this. Okay. I missed the factor, which is minus 2. Yeah. So in fact, okay. So this expression is something like this, but up to the sign and up to a factor 2. Because the true formula is that if x was stationary, then this would have, it would not depend on t, right? So the right-hand side would just be minus 2, the integral of f chi dq. So that we would have, okay, let's say, in cases, chi in direction E1. So in cases where, for some reason, you know that you have a stationary corrector, then you have this expression of gamma bar in terms of chi. And in situations where you don't know that chi is stationary, then you have to replace this by an ergodic average. But, okay? Okay. And so, if I summarize, the fluctuation-dissipation theorem was telling us that the derivative at lambda equals 0 of nu lambda of f is this operator gamma bar of f. And if I rewrite it in this way, this is minus 2 times the integral of f chi dot E1 dq. So I can summarize if you want. Summary. So first of all, a short way to express this is just to say that the derivative of the steady state is given by minus 2 times the corrector in the direction in which you perturb the diffusion. So the derivative of the steady state is the corrector up to this minus 2. Okay? So this is the fluctuation-dissipation theorem. Okay, so the fluctuation-dissipation theorem, in the case of diffusions in a random environment, it reads the derivative of the steady state is given by the corrector. And we proved it in the case of a uniformly elliptic, smooth environment with a finite range of dependence. Okay? And the correct interpretation of this formula, which requires a correct interpretation of this formula, is that in general, this will not be a product in L2, but you should think of this as a duality product of chi, which belongs to H1, and F, which belongs to H minus 1. So that equality is an equality that should be interpreted in the space H1. Or maybe not, because when we played with H minus 1, we played with H minus 1 infinity. So this is in duality. Maybe it would be better to say in duality with H minus 1 infinity, with respect to H minus 1 infinity. Okay, so the meaning of this, the correct interpretation of this is you take the product on a certain function in H minus 1 infinity, and then this is well defined, and you should define nu lambda actually on H minus 1 infinity, and then prove that. Okay. So I will stop here. Thank you.
So in your poster, you have these pictures of papers.
These were simulations of disordered environments.
So what kind of?
They were. There are two pictures in the poster. One is a stationary disordered environment, and the other one is it's not stationary because it is like a shear flow. It is only stationary in the vertical direction, and it's not there is a it is stationary in one direction only. It's supposed to represent an environment in which there is a drift. There is a preferred direction, clearly. Now, you want to know how I got these simulations. So these simulations were indeed, one of them is just paper. So I don't know how good this is, but and I don't even know the English word. So like this. And the other one is it's a table I have. It's a photo of a piece of the table, but the table is actually layered. It's outside, and it was painted, but the paint was damaged by wind, whatever we get, wind, rain, etc. So I think that this second thing is it's a rather good model for disordered environment. I think that this is actually probably much closer to what is a true physical disordered environment than any simulation you can run.
Question on this remark. When you say phi is stationary with respect to spaceship.
No, I mean that I want a function. I want, let's say, I define k. Oh, okay, so what I want is to define chi of x omega in such a way. I know it's gradient, and so yeah, maybe I was not very precise. So let's see. You use this theorem, and then you get some function, which I write like this. Okay. You don't look happy. So let u of omega be a solution of this equation. So you write this equation. Yeah, it depends on omega. It's a random field. Okay? So the solution of this equation. Okay? Now, you take chi of x omega such that gradient of chi equals u of omega. And this you can do. For example, in this way. And then the question, what I would call a stationary solution. So a stationary solution would be a function chi of omega which solves this equation. So that when you take the gradient of chi of x dot omega, you get u of omega. Okay? So that this problem has a solution is easy. But it's not clear that whether this problem has a solution. In general, this problem doesn't have a solution. Here it's a dot. And so, okay, so what I write in that remark is that assuming that there is a chi of omega that satisfies this, which I call the stationary corrector, then the expression which is there is just doesn't depend on time, and it coincides with this integral.
Okay, must you rewrite this chi of x omega zero s omega as chi of, let's say, 0.
Then,
You can replace comma by dot.
and this is the omega
Yeah, omega.
of s. This is stationary with low q. Omega of s is a stationary process. So I'm taking the mean. So this thing doesn't depend on t. And then I don't have to send t to infinity. And the value is this. Also. Yeah. So this was. Let's say we wanted to express gamma bar with the corrector, and then it's easy. You easily find this expression. For instance, in the periodic setting. Then you have a stationary corrector. Then you find this expression. It's not difficult. And then the question was how to make sense of this expression in the general case, because this, taken as it is written here, doesn't have any meaning, because chi is not stationary. So one way to give a meaning is to use this finite time approximation. and then it works. You can prove things. Now, another way to give a meaning of this expression is to say that you are looking at chi as a distribution in H1, and F is in H minus 1, and this is the duality product, which is also a possibility. Well, I'm happy you are happy. Are you all happy? Okay, so
Okay, then let's
thank you very much.